This problem is an application of Faraday's law. Where did I draw that? So you have some loop of dimensions A and B, and that's supposed to be a rectangle. You have some loop of dimensions A and B, and the magnetic field is perpendicular parallel to the normal of the loop surface, so that's perpendicular with the plane, and it could be up, it could be down, it doesn't matter. I'm just choosing into the plane here. This is uniform everywhere. Okay, so sometime later this half of the loop gets bent and pushed into the other side, so you end up with this bent little loop like that in the same field. So what is the induced EMF in the situation? Well, Faraday's law says the induced EMF is equal to negative in the number of loops times the time rate of change of the magnetic flux with time rate of change of magnetic flux. Well, in this case, n equals 1 because there's just one loop. So I can write that as negative d dt, and I can write the flux as b a cosine phi. Because the flux is just b dot a, the dot product of b and a, or b a cosine phi. Well, remember the area normal vector points normal to the surface of the loop, so it's either out of the plane or into the plane of the paper, which is exactly the same direction as the if it's out of the plane and we chose the magnetic field to be into the plane, then there will be a negative there. It would be a 180 degree angle. But the negative's not going to matter here because we're just worried about the absolute value. So I'm going to say phi equals 0 and cosine phi equals 1. So the orientation is not changing. What's interesting about this problem is it highlights that you can be changing the magnetic field, you can be changing the area, or you can be changing the orientation. Either way, you end up, either of those three ways, you end up with an induced EMF. Well, the orientation is not changing, so the EMF is equal to negative d dt BA. Is the area is changing? Is the magnetic field changing? No, it's not. It's being held constant. So negative b dA dt. So how is the area changing? Well, we don't know. We don't know at what rate the area changes. Does it, if we're looking at area versus time, does it take a linear path? Does it take an exponential path? Does it do some kind of weird thing? All we know is it gets to 0. A final equals 0 and A initial equals A times B. We don't know how it gets there. So we can't perform the derivative on a function that is not defined to us. Except the problem does not ask for the EMF, the problem asks for the average EMF. Because the EMF induced would be changing as this function of area changed, because the derivative is just the slope of this. So whatever the function is getting from the original area to the final area doesn't matter, because the average is just going to be delta A over delta T. The average is going to be the slope of the linear path, the constant slope. Okay, so anyways, that equals negative B delta A over delta T. And negative B equals A final minus A initial over delta T. And we know A final is 0. So the average EMF is equal to positive B A initial over delta T, or it's equal to B AB over delta T. Now, conveniently, the negative sign went away. That's nice for us, but would it have mattered if it didn't? No, it wouldn't matter, because if you ended up with a negative sign, it's just because of the way you chose the directions. And in most of these Faraday's law problems, the direction is not going to play a role. It's not going to matter. We're just looking for absolute values. So this is then equal to 0.65 Tesla times 0.20 meters times 0.35 meters all over delta t, which is 0.18 seconds. So the average EMF comes out to 0.253 volts.